In this video, I'm going to be explaining the atan2 function and the reason it's used over the classical arctangent function when parameterizing complex numbers, which are a big part of quantum computing and physics in general. So let's assume we're given a complex number, z, right, in the complex numbers. Every complex number has a real and an imaginary term. So for simplicity, we'll redefine z as an ordered pair, a and b, where a is just the real term and b is the imaginary term. And so what we actually have now is just a point written in rectangular coordinates. And so what we want to do is figure out how to convert this point into polar coordinates. Right, so we have a and b, right, which is just your traditional Cartesian plane x and y coordinates, and we want to figure out how to get it in polar coordinates, so in terms of an angle and a magnitude. So what we're really looking for here is some kind of function. We'll just call it 2 polar. That takes a pair of rectangular coordinates, a, b, and sends them to a pair of polar coordinates, r, theta. And we restrict theta to be in this codomain here, just so, or in this range here, just so that we don't have an infinite number of possible solutions. So what we're trying to do is figure out how to rewrite z, which is a plus bi, into r e to the power of I theta. Where, again, r is the magnitude of the vector, and theta is the angle from the positive x-axis. So we have by definition that a is r cosine theta, b is r sine theta, and just from basic algebra, right, we can figure out that theta is just arctangent of b over a, and the magnitude r is just the square root of a squared plus b squared, just your traditional vector norm. And so at this point it may seem like we're done, right? It's just that simple. But don't be fooled, because we have to remember that arctangent, the domain is just the real numbers, right? But the range is limited to negative pi over 2 to pi over 2, which is just the right portion of the Cartesian plane. And that's periodic in pi, not 2 pi. Again, which limits us to only quadrants 1 and 4 of the Cartesian plane. So let's see why this is actually a problem. So let's say we have a complex number, 1 plus 1i, right? So our magnitude of that vector is just going to be the square root of 1 squared plus 1 squared, right, which is just square root of 2. And then theta is just going to be, right, from up here, we'll use this rule, arctangent of b over a, so arctangent 1 over 1, which is just pi over 4, right? And this looks okay, right? Like, this is theta, right? So this would be pi over 4, that's what the angle would be, right? Okay, so, all's well and good. But what if z was negative 1 minus 1i, right? So this is a completely different complex number. Again, the magnitude is just going to be the square root of a squared plus b squared, which again gives us square root of 2, same as before. And theta, again, is just going to be arctangent of b over a, which is just negative 1 over 1, which is arctangent of 1, which is, again, pi over 4. And this can't be right, because this procedure is producing the exact same polar coordinates as the complex number 1 plus 1i. So clearly something is going wrong here. And the issue is that arctangent is a function of a single number. So it doesn't have access to the information stored in the signs of a and b, right? Because what you pass into arctangent is b over a, which is equivalent to negative b over negative a. So that's why it doesn't have access to that sign information. It just takes in a single real number. So if we naively define, this function 2 polar with the classic arctangent, then the function is going to fail to be injective, right? We just found a counterexample. We have two complex numbers that are two different complex numbers that map to the same coordinate, to map to the same r and theta. So this is more of an in-depth example, right? So with the examples from before. So when we want to parameterize -1 minus 1i, right? That vector is over here, right, in quadrant 3. So what we really want is the angle from the positive x-axis, right? So what we're really looking for is this phi angle here. But since arctangent is restricted to this side of the Cartesian plane, what it'll actually do is flip it over, right, into it'll flip quadrant 3 into quadrant 1, and then it'll calculate theta over here because it uses the same, since b and a are -1 and -1, when you plug them into arctangent, right, you're just plugging in b over a, which is -1 over -1, which is equal to 1 over 1, which is 1. So when you take the arctangent of 1 over 1, you just get pi over 4. So that's essentially the issue. Arctangent is restricting us to this side of the plane, so we can't actually parameterize the true direction of this complex number here. It's treating -1 minus 1i as the same as 1 plus 1i. So that's why we have this function atan2, right? And that resolves this ambiguity by taking not one input as arctangent does, but both inputs, a and b, as separate arguments. So this is the exact function, right? You can see there's a lot of different cases here, but note that it actually builds on top of the classic arctangent function. It kind of just, think of it as, it kind of just adds corrections to what arctangent would usually give or produce, depending on what the signs of a and b are, i.e. what quadrant that point or vector is in. So we can verify how that works here. So if we let z1 be the original 1 plus 1i and z2 be -1 minus 1i, if we define two polar with just the traditional arctangent, right, we see that we just get the polar coordinates 1 and pi over 4. And that which produces the exact same parameterization with -1, -1, right? We get 1 and pi over 4 again here. So that's why this is a problem, because two polar is no longer injective. So yeah, it's clearly not injective. Two different complex numbers are mapping to the same polar coordinates. Now, if we use atan2, then we'll see that when we replace the classic arctangent for the complex number 1 plus 1i, if we go back, so a is 1 and b is 1. So let's see, what does that mean? A is x, right, and b is y. So since they're both positive, so x is positive, it's just going to be the normal classic arctangent. So that is what we do, right? So we just plug in the regular arctangent, and again, you just get the same answer from before, 1 pi over 4. And then for the -1 minus 1i, when we use atan2 instead of the classic arctangent, what we see is that x is negative and y is negative, right? A is negative and b is negative. So what we're going to use is, instead we're going to use the classic arctangent, b over a, and subtract pi from that, which is what we do here. Classic arctangent and subtract pi. So the classic arctangent, right, pi over 4, we subtract pi, that gives us -3 over 4. And that is exactly what we're looking for here, right? That's exactly what this phi was here. And so, hooray, right? It works. So we're now able to parameterize a complex number and take advantage of the full Cartesian plane here, no longer being restricted to the right side, which gives us this non-injectivity, which is a problem. So alas, we've found a bijective map from rectangular coordinates to polar coordinates, such that unique rectangular coordinates produce unique polar coordinates. So I hope that this was helpful. Please leave a comment if something is not clear, or if there's something that I can explain better. I would really like to get better at doing this. So thank you.